In this video, I'll be configuring the Venturi tube, the one that you see here, before using it. The Venturi tube has two taps. I'll get closer to show you the taps that I'm referring to. So it has this tap and this tap. Both of them are connected to impulse lines, which I will get to in a moment. So the Venturi tube has a cross section with a wider cross section and a narrower cross section, and then the narrow cross section becomes wide again. The wider cross section to which this tap is connected will have a higher pressure than the narrow cross section to which this tap is connected. The flow, for laminar flow, the flow should be the same across the Venturi tube. The flow rate, that is, for laminar flow. The pressure at this cross section will be larger than here. So the speed of the fluid, in this case water, will be lower at this cross section than here, than at the narrow cross section. So at the narrow cross section, the speed of the fluid will be larger than at the larger cross section, because the pressure here is higher and here it's lower. So that will allow the fluid to accelerate once it gets to the narrower cross section. So what I have done as part of my configuration is I have connected the Venturi tube to a pressure differential indicator through a 3-valve manifold, the one that you see here. Of course, I have went through the bleeding process. So in order to bleed my Venturi tube, I've connected these two impulse lines to my 3-valve manifold and these two impulse lines. These are very long impulse lines, and they will affect the measurements that will be made by my differential pressure indicator. However, in order to improve my setup, or to optimize my setup, I have made an approximation. I didn't make exact measurements, but I have tried to make as much as possible these two as equal as possible, because I don't have a ruler here, and I don't have anyone holding those tubes for me because they do twist. So I tried to make these two as equal to each other as possible, and I tried to make these two lines as equal to each other, because that will affect the resistance of that my water has to overcome to reach my sensor. For the bleeding operation, what I have done is that, so first I should let you know that the higher pressure is here, and that's going onto the right, and the low pressure is here, that's going onto the left side of my 3-valve manifold. So since here I have metallic taps, I have metallic couplers, whereas here I don't have any couplers because these are plastic rings, and the same at the bottom. So the higher pressure goes at the back, and the low pressure goes here. So the back is connected to the tap that is connected to the high, to the higher, to the larger cross section, whereas this one is connected to the lower cross section. So in order to bleed, what I have done is I've closed this valve. So I'll close it right now just to show you what would happen. So right now, this equalizer valve is closed and both of these are open. This valve and this valve are open. This is the high pressure valve, high pressure inlet, and this is the low pressure inlet. So this is giving me a pressure differential 1.71 kilopascals. I put it in kilopascals. So the difference between the two cross sections that have different dimensions is currently 1.7. So this is when these two valves. I shouldn't be moving things because that will affect my readings. These two valves are open right now. What I'm going to do right now, I'm going to close this valve. I'm going to close this valve, and I'm going to open the equalizer valve. I'm going to open this valve now. Okay. So now that the low pressure valve is closed, there's no more, I'm not getting any more pressure in here. Well, coming out of here. So the only pressure that I'm getting is from this one. And it's going here and it's going into the one that was the low pressure. So the pressure here and here should be now the same because I've opened the equalizer and I've closed this valve. So I'm not getting any more pressure from here going into this valve. What I'm getting is pressure from the high pressure valve going into the equalizer. So this tube and this tube should have the same pressure. If I take a look at the reading here, I'm getting 0. This makes sense because now I'm not getting any more pressure from here, I'm getting the pressure only from here. And so since this valve is open, the pressure in both of these tubes should be the same, and that's why my differential pressure indicator is showing 0. So I'm just going to go back, and that's how I actually did my bleeding operation and my zeroing. The bleeding doesn't have to be done this way, but for the zeroing, it's important because both pressures have to be equal in both of these tubes in order for me to get 0 at the differential pressure indicator. So now I'm just gonna open this valve. And close this one. Okay, so no more water is passing here. So this now and this, so these two pipes are isolated from each other, or this and this are isolated from each other. There is no exchange between any of these two. Once this valve is closed, the equalizer valve, there's no more connection. There's no connection between these two. They're isolated from each other. So now I should see a pressure difference. And it's exactly the reading that I had earlier, 1.71. So now what I would like to do is verify if the reading that I'm getting here, of course, because in order to set it up correctly, in order to set the Venturi tube correctly, the pressure difference at these two cross sections So the pressure difference between these two cross sections should correspond to a flow rate. And that we can see it in the familiarization book. This is the graph that I have to refer to when I have to check against when I look at the pressure difference between these two taps and the flow rate. So I'm going to make a reading right now on my rotometer. So the reading right now is it's probably well, very close to 10, if not exactly at 10. So that is 10 liters per minute. Okay, 10 liters per minute. And for 10 liters per minute, I am getting, I'm going to turn to my, getting 1.71 kPa, kilopascals. And it's not changing. So what I'm going to do right now, I'm going to increase the pumping action, and I'm going to try to get it to 20. Try to get the Oh, I am very close to 20 now. Yep, it's very, very close to 20. So let's take a look at the reading on my transmitter. .7. 6 point 6.79 kilopascals in that region. So that's a second reading. Of course, just like what we did with the hydrostat, what I did in the hydrostatic when measuring the hydrostatic pressure in my column, here again I have to take several readings in order to ensure that the setup for my Venturi tube is correct. So I may have to take 4, 5, 6, 7, 10, 100 readings. That really depends on how accurate I want to be. So with the rotometer that I have here, it's not so easy to take so many readings. But again, it's doable. So what I'm going to do is take one more reading. So I'm going to increase the pumping action and try to get it to 30 liters per minute. So not yet there. A little bit more. Just a little bit more. Not exactly. Try to make it as exact as I can. Not exactly at 30, but very, very close. So let's take a look at what my differential transmitter is saying. 12.72 approximately kPa. So as I said earlier, you may have to take several values and to check it against the graph that I just showed you to see if the pressure difference that you're getting for your Venturi tube corresponds to the flow rate through the Venturi tube.